Hello, I'm Shabana K. from Indian Institute of Technology, Palakkad, here to present our paper, Curriculum Tutor and Adaptive Algorithm for Mastering a Curriculum. Let me first introduce the research problem being addressed. In traditional classroom and MOOC setting, the same lessons in a fixed sequence are delivered to the entire student population, irrespective of their learning background or abilities. Whereas in adaptive sequencing, the lesson sequences are customized based on the individual learning characteristics of each student. Personalizing education using adaptive activity sequencing has shown to result in an improvement in learning gains, apart from providing a more engaging learning experience for the students. We specifically consider the learning by doing setting, where concepts are learned by doing activities. Teaching mathematical concepts through solving problems is a real-world example that fits in this framework. Let me first introduce some of the terminology being used. A concept is defined as a representational unit of educational content. The question bank of activities contains a collection of question answer pairs for each concept. A curriculum graph models the concept interdependencies with the nodes representing the concepts and edges representing the prerequisite relationships among the concepts. For instance, a directed edge from A to B indicates that the concept A is a prerequisite for learning concept B. The zone of proximal development, or ZPD, represents the set of concepts that are on the student's knowledge boundary. In the figure, note that C, D, and E form the ZPD as all of the prerequisite concepts have been learned. Multi-arm-banded problem consists of a fixed set of actions or arms and an unknown reward distribution associated with each arm. The aim is to select actions such that the long-term cumulative reward is maximized. The key challenge in this problem is to balance exploiting the information that has already been gained about the effectiveness of each action and exploring actions where the estimates about their value are still relatively uncertain. This is referred to as the exploration-exploitation trade-off. The actions which are more effective and can earn larger rewards are eventually learned over time. Multi-arm bandits find application in several domains, such as in ad selection and placement in web pages, as well as in AI-based computer game agents such as AlphaGo. In the multi-arm bandit framework for adaptive sequencing, the activities or lessons in the ZPD form the arms and rewards are computed based on student responses. The system maintains an estimate of the learning progress associated with each concept in the ZPD, based on which it decides the next activity to be offered to the student. In the process of maximizing cumulative rewards, the multi-embedded framework would pick activities from the concepts that the student tends to learn faster, thereby generating a personalized activity sequence. This formulation is less reliant on the underlying model of student learning and can therefore better adapt to different individual learning behaviors. A schematic diagram of the framework has been shown here. In this work, we assume access to a concept graph for the curriculum to be mastered, as well as a question bank of activities for each concept. Let us now look at the prior work and then discuss the research gaps which are addressed in our work. Zone of proximal development and empirical success is based on the multi-embedded framework for adaptive activity sequencing, where preconditions between activities are provided in the form of an expert-defined curriculum graph. At each time step, ZPD selects the next activity A' based on the normalized weights of activities WA' in the ZPD, as well as an exploration factor gamma. The correctness of students' response to an activity A', the ith attempt, CA'(I), is a binary random variable which takes a value of 1 for a correct response and 0 for incorrect response. The reward is computed by taking the difference of the number of successes in the last D/2 samples with the D/2 previous samples, where D is the window size. The reward provides an empirical measure of how the success rate is increasing. The reward becomes close to 0 when either a concept has been mastered or the student struggles to master it. A high positive reward indicates good learning progress. Later, a novel system, program to tutor, was proposed that combines automatic curriculum ordering with ZPDES for automatically and adaptively advancing a student through a curriculum. Here, a sliding window average is used for inferring mastery, where a concept is determined to be mastered when the accuracy over the past T attempts reaches above a specified threshold T. The major drawback of ZPDES is the use of many hyperparameters such as D, W0, gamma, beta, and eta. Using fixed values for these hyperparameters will have an adverse effect on personalization, whereas tuning these hyperparameters for different individuals is an additional computational overhead and a time-consuming process. Thus, the main issue with ZPDES is the use of too many hyperparameters that require tuning. This hurts personalization and also adds to the computational overhead. Our approach is to decompose the adaptive activity sequencing problem into the following two subproblems, namely activity selection to take care of the exploration versus exploitation trade-off and detection of mastery to handle the non-stationarity of the student responses. The tutoring algorithm at each time step has to select an activity that offers higher learning progress to the student. We consider the case where the rewards are binary. That is, a reward of 1 is obtained if an activity related to the selected concept is correctly performed and otherwise 0. The problem can now be modeled as a Bernoulli multi-banded with the concepts in the ZPD forming the arms. Here, a reward of 1 is obtained with probability P that is dependent on the knowledge level of the associated concept or arm. The tutoring algorithm has to infer whether a concept has been mastered based on the sequence of student responses. The non-stationarity of student responses resulting from the student learning a concept is addressed here. Determining whether a concept has been mastered helps to avoid over-practicing, which leads to a drop in the learning gains, and under-practicing that results in the concept not being learned. For detecting mastery, each concept is assumed to be associated with two states, learned and not learned. The probability of getting a correct response in the not learned state is given by P guess, whereas the probability of a student answering incorrectly while in the learned state is P slip. The reward distribution is now piecewise stationary. That is, it remains constant for a certain period and shifts at some unknown time step referred to as a change point that corresponds to the transition from the not learned to learned state. Detection of mastery of a concept can therefore be modeled as a change point detection problem, which can be described as follows. Given a sequence of observed random variables, x1, x2, etc., having a distribution function p0 until a change occurs at an unknown time point lambda, after which the observations have another distribution p1 with p0 not equal to p1. A sequential change point detection procedure is identified with a stopping time tau for an observed sequence. That is, the time of alarm tau at which it is declared that a change has occurred. The average detection delay and false alarm rate of the procedure can be defined as shown. A good detection procedure should have small values of average detection delay with a low false alarm rate. Our method curriculum tutor is based on the framework of multi-banded and change point detection. It employs a standard banded algorithm for activity selection and has no hyperparameters to be tuned. The method has also been shown to provide better learning gains as compared to prior methods. Let me now describe our algorithm curriculum tutor that combines a Bernoulli multi-banded algorithm with a change point detection technique for adaptive activity sequencing to master a curriculum. Curriculum tutor uses the KLUCB algorithm to perform activity selection, while QSIM is used for change point detection. KLUCB is a Bernoulli multi-banded algorithm which has been shown to have better performance bounds than other banded algorithms in the Bernoulli setting. The algorithm maintains an upper confidence bound for each arm. The arm with the highest UCB is selected at every round. QSIM uses the log likelihood ratio to test the hypothesis that a change occurred at the point lambda and that there is no change at all. Here P0 and P1 are the pre-change and post-change probability density functions respectively. The maximum LLR statistic UN is compared with a threshold h, and a change is detected when the value of un exceeds h. When h greater than 0 and the observations are independent and identically distributed, un can be replaced by the statistic u tilde n, which can be computed recursively. It has been proved that in the IID case, QSUM minimizes the worst case average detection delay among all detection algorithms for a fixed false alarm rate. With user-defined PGUS and PSLIP, the pre and post-change distributions can be defined as shown here. The curriculum tutor algorithm has been described here. The algorithm maintains a ZPD at each time step based on which activities are presented to the student. A concept is removed from the ZPD when it is determined to have been mastered. The ZPD is then updated with concepts in the not learned state, all of whose prerequisites are in the learned state. This continues until the student has mastered all the concepts in the curriculum graph. I will now describe the experimental setup to evaluate our algorithm in the domain of two-operand addition with simulated students. The curriculum graph for the domain of two-operand addition up to a maximum of 4 digits was generated using the trace-based framework proposed by Anderson and others. Here, actions taken to solve a problem are labeled to build an execution trace, and the traces are then ordered to build the concept graph. Towards this, 4 basic operations were identified to be required to solve an integer addition problem, which are 1-digit addition without a carry, 1-digit addition with a carry, writing a carry, and bringing down a final carry. Here we can see how the problems can be decomposed into these basic skills and expressed as traces. The traces are then ordered by complexity based on the n-gram-based partial ordering as follows. With n as a positive integer, a trace T1 is said to be at least as complex as trace T2 if every n-gram of trace T2 is also present in trace T1. The curriculum graph is then generated based on these orderings. Here is the curriculum graph that was generated with n equal to 3. Students were simulated using 4 popular knowledge tracing models. For each student model, separate knowledge components were defined corresponding to addition of different lengths, presence of carry, and overflow. In Bayesian knowledge tracing, a student's knowledge state is modeled as a 2-state hidden Markov model, 1 per knowledge component or skill, where the skill is either mastered by the student or not. Prerequisites between knowledge components were enforced by varying the transition probability between states, depending on whether the prerequisites were learned or not. In learning factors analysis, the probability P of a student performing correctly on an activity is modeled as a logistic function with parameters such as student learning rate, the number of times the knowledge component has been used, difficulty level of activity, etc. In performance factors analysis, the probability P of a student performing correctly on an activity is modeled as a logistic function with parameters such as the number of times the knowledge component has been used correctly or incorrectly, student learning rate, difficulty level of activity, etc. The fourth model integrates knowledge tracing with item response theory. Here the student's knowledge is represented as a HMM with binary states. In each state, the probability of answering a question correctly is modeled as a logistic function with an intercept term which is dependent on that state. For the experiment, the best value of ZPDS hyperparameters were found using grid search separately for each student model. The false alarm rate for detecting mastery was set as 5 to the power minus 5. For the sliding window, the window size was set as 8 and the accuracy threshold as 0.7. Thus, out of the last 8 activities, the student has to get at least 6 of them correct in order to infer that the concept has been mastered. For QSUM, the threshold H was set as ln e to the power minus e to the power 4, and PGUS and PSLIP for each concept were sampled from beta distribution with parameters 20 and 40. The following 2 scenarios were simulated using the 4 different student models. In scenario 1, student does not struggle with any of the concepts. Here, similar model parameters such as transition probabilities, learning coefficients, intercept values, etc., were used for knowledge components of similar complexity. The parameter values were made smaller with increasing complexity. Whereas in scenario 2, the student struggles with a few concepts in the intermediate phase. Here, the student models use lower parameter values for the KC, 3-digit addition without carry and overflow, as compared to scenario 1. Here we present the experimental results that compare the performance of 3 tutoring algorithms, namely Curriculum Tutor, ZPDAS, and Blocking. Blocking is a basic scheduling scheme where activities associated with the same concept are presented to a student until the concept is mastered. It uses a sliding window to infer mastery. The fraction of concepts in the curriculum graph that was mastered by the student over a given number of questions was computed in each case. As we can see in both the scenarios with all the 4 student models, the learning curves of Curriculum Tutor lie above those of ZPDAS and Blocking, implying higher learning gains. To conclude, we have proposed Curriculum Tutor, a novel multi-arm banded and change point detection based algorithm for adaptive activity sequencing to master a curriculum in the learning by doing setting. Simulation results show that Curriculum Tutor significantly outperforms prior approaches in the benchmark domain of 2-operand addition up to a maximum of 4 digits. Future work on this problem includes accounting for forgetting of a learned concept, considering partial credit scores, and accommodating for activities with varying levels of difficulty associated with the concept. Thank you.